Welcome back. If you watched the first part of this video, we're working on properties of functions, or mainly definitions of functions, and how to analyze functions using these certain properties. If this is new, well then, welcome. We want to talk about even functions, odd functions, and those that are neither even or odd. A function is even if f of negative x is equal to f of x. That's all there is to it. If you can substitute negative x into your function, simplify it, and get the same as your original function f of x, then you have an even function. Okay? Now graphically, what does that mean? Well, let's draw that idea. Okay? So it's saying if I plug negative x into my function, and I plug positive x into my function, I get the same y value. That's what it says. So if this is my y value for negative x, then this is my y value for positive x. And y'all, that's true for every x. So if I picked another x value and said that it was right here, then that x value positive would be right there. Okay, so that's true for all x, which might give us a graph, and this certainly isn't the only one that looks like that. So I came to this conclusion on the second line. This also means the graph is symmetric about the y-axis. And notice it is. If I put a mirror right here down the y-axis, the graph is the same on both sides. So a mirror reflection. Another way to think about it is a piece of paper. If you fold your paper along the y-axis, then the right side will land on top of the left side. So that's what it means for a function to be even. The first line of the definition is algebraic, and we'll have to do problems involving that. The second is geometric, and you see a picture of exactly what I mean by that. Okay? So let's try this again with the idea of an odd function. So algebraically, what odd means is if I substitute negative x for every x in my function and simplify it, it gives me negative f of x, which just means the opposite of my original function, f of x. Okay? Now graphically, what in the world does that mean? If I have a negative x over here and a positive x over here, well, let's just say my negative x is this value right here, just like we did before. Then when I plug in positive x, which is over here on the right hand side of my definition, I get the opposite of that. So it would be the same height but down here. Okay, and it's true for every point on your graph. So let's just say this is another negative x value, and let's just say that answer was right here. Well, that same positive x value over here would give you that answer right there. And a way to sketch or connect the dots might look something like that. So your first thought might be this ought to be symmetric about the x-axis. Well, that's not true at all. It's symmetric about this point right here on the origin. Okay. Matter of fact, if you had a graph symmetric about the x-axis, say that guy right there, it's not a function. Okay, so we don't have terminology for symmetric about the x-axis when we're talking about functions, because that's not a function. It's mathematical, just not a function. So back to what we can talk about. Even functions are symmetric about the y-axis. Odd functions are symmetric about the origin. Now, how do you handle that in terms of a reflection? Well, one way you can do it is if you visually folded along the y-axis here and then took that piece of paper and folded along the x-axis. You can picture this in your mind. This will land on top of this. These pieces will land right on top of each other. Sometimes that's hard to visualize. So what I suggest students do is rotate. You can picture if you rotated this top left piece, which is called quadrant 2, all the way around 180 degrees this way to quadrant 4, this piece would land right on top of this piece and line up. Now, my rough sketch doesn't do that, but it would if you really had an odd function. So practice problems. Are the following functions even, odd, or neither? Now, one option is you could graph these and determine if they are symmetric about the y-axis, which means it would be even, or symmetric about the origin, which means it would be odd. But that's way more work than you're required to do. The best thing to do is do the algebra. In other words, what I want you to do is substitute negative x in everywhere there's an x. So that's the first step. Substitute negative x for x and then simplify. So I'm going to remove the x in x to the third and replace it with negative x to the third. Parentheses required here because you're raising not only the x to the third but the whole negative x. So minus 2 also times negative x. So that's step 1. Substitute in negative x for x. Step 2 is simplify. Okay, negative x to the third. Well, a negative times a negative times a negative, because that's what to the third means, is multiply those things 3 times. It gives me negative. X to the third gives me x to the third. And then a negative 2 times a negative x is a plus 2x. And the last step is you compare to the original. Okay, now is this the same as the original? Well, no. It's a negative x to the third plus 2x. The original is x to the third minus 2x. Is it the opposite of the original? Well, yes, because if I multiply this entire thing by a negative 1, it'd be negative x to the third plus 2x, which means you have an odd function. Okay, so if you get the opposite of the original, in other words, you're taking the original and multiplying it by negative 1, then you're dealing with an odd function. Okay, well, let's try the next example. Steps are the same. I'm substituting in negative x everywhere there's an x. And so notice the only x in this function is right here, x to the fourth. So I'm going to say 3 times negative x to the fourth minus 2. And then I'm going to simplify. So step 2 is simplify. Now if you take a negative number and you raise it to the fourth power, it turns positive, right? And then the x to the fourth minus 2. And now you compare. Okay, well, compared to the original, this is exactly the same. Well, if you go back and you look at your definition for even and odd, notice that's exactly what an even function, watch me just spin it all around, that's exactly what an even function is you get the original function back, f of x. So I go back, and if you get the same, again, that means you're dealing with an even function. So if we were to graph this, it would be symmetric about the y-axis, but we're not graphing. They just want us to do the algebra to find out if this is even, odd, or possibly neither. So our last example, again, I start the same every time. I plug in negative x for x. Okay, and then step 2, simplify. So a negative x times a negative x is going to be x squared, or in other words, negative x to the second power. And negative 5 times the negative x is a plus 5x, and then plus 2. So I asked myself, is this the same as the original function? Well, no, because the negative is 5 is in the original function. This is a positive 5, so it's not even. Is this the opposite of the original function? Well, if I multiply the original function by a negative 1, I would get negative x squared plus 5x minus 2. So, nope, it's not opposite the original function, which basically means that this function is neither even or odd. And really, honestly, most functions are neither even or odd. It's a special property that some functions have. It makes it easier to graph the function if you know this ahead of time. But most functions, if you just randomly made one up or randomly grabbed one out of a book, would not be even or odd. It would be neither. Now, there's some conclusions we can come to here. All of the functions I gave you are polynomial functions. Now, officially, from previous classes, you may have an idea of what a polynomial is. It's terms being added or subtracted. There's specifics about the exponents have to be positive whole numbers or 0. You can't have square roots, things like that. But if you have a polynomial function, an easy way to do this is you can check out the exponents to your variables. So check it out. You got an x to the third. Right here you got an x to the first. Both of those are odd exponents. right? Try it again. Check this out. You've got an x to the 4th, and then right here you don't have an exit at all. So that's like an x to the 0. 0 is an even number. So those are even exponents, which means you have an even function. And then finally this last one, you have a square exponent, you have a 1 exponent, and you have a 0 exponent. Okay? So again, if for your notes purposes, what I'm saying is right here, this is like an x to the 0. So that's an even number. This is like an x to the 1st right here. That's an odd number. And this, of course, is an x squared, which is an even number, which gives you neither. So that's a nice way to do it. Now, I didn't show you that right off the bat because that only applies to polynomial functions. And in your math career, you'll run into many types of functions that are not polynomial functions. And so to show that they're even, odd, or possibly neither, you would have to do the steps that we just did. Now I would like to look at a graph and determine whether the graph is even, odd, or neither. Now remember, an even function is symmetric about the y-axis. So let's take a look at all three of these. If you could fold your piece of paper along the y-axis, that means it's even. So if I fold right along here, and I'm sliding my better yet, let's do this the right way. Right along here, right? If I fold my piece of paper there, will one side land on the other side? Well, no. So that is definitely not even. If I fold my piece of paper here, will the right side of the paper land on top of the left? Nope. So that guy's not even either. But if I fold my piece of paper right here, check this guy out. This right hump will land right on top of this left hump, okay? And I will get an even function. So we know that this guy is even, and we know these two guys are not. Okay? Now let's look again. Let's see if we can find an odd function. Okay, so I'm going to erase real quick my guidelines here. Alright, now an odd function, remember you have to fold a piece of paper twice. So you would have to fold along the x-axis and then fold again along the y-axis. And then one piece of graph will end on another piece of the graph. Okay? Or you can say, hey, if I rotate this quadrant over here 180 degrees to this quadrant, does this red graph show up over here as well? And the fact is, no, it doesn't. So this is not odd. Okay? So let's try this again. If I take my piece of paper and fold here, and then fold here again, I know this is hard to see, does this land on top of this? So does this quadrant roll around and land here? Yes. Does this quadrant roll around and land here? Yes. So that means that this is an odd function. I know that's harder to see. Odd is harder to see. So you either fold twice in your mind or you rotate this quadrant to here and it matches, and you also rotate this quadrant to here and it matches. Okay? Now finally, if it doesn't meet either one of these requirements, that means you're dealing with a neither function. So the first one is neither, the second one is odd, and the third one is even. Alright, so I have another practice problem for you. It says use the graph of f to determine each of the following. Where applicable, use interval notation. Okay, so let's remind ourselves, when do we need interval notation? Well, interval notation happens for domain, range, increasing, decreasing, constant, and sometimes other situations. But it looks like when I scan down, I'm going to circle these for domain, range. X and Y intercepts are just points, right? Increasing, decreasing, constant. And that appears to be it. Okay? Alright, so the rest of our answers will probably be points or just numbers. And we'll handle that individually as we go down. Remember, domain is left to right. So the leftmost x value on my graph all the way to the rightmost x value on my graph. And I must include any breaks or holes in between if I have any. Well, notice the leftmost x value. There's nothing out here until I get to, looks like -8. Notice that point is very filled in, so we include it. So we're talking about -8, no holes, And it looks like it goes to the right forever, right? Because this arrow goes down and to the right forever. So how far to the right is that? Forever. So -8 to infinity. Now, infinity's not looking so hot right there. Range is low to high. So how low does this graph go? Again, that arrow says it goes down forever. So the low is -infinity. And how high does it go? It looks like it goes up to 3 to me with horizontal line right there. 3, and that 3 is included because there are a bunch of points that represent 3. Okay, x-intercepts, let's label those. We can do that right on the graph as well. This point right here is an x-intercept because it crosses the x-axis, and this point right here is an x-intercept because it crosses the x-axis. So it's just two different answers. Your book would put -6 for the left one and 6 for the right one. I like them in point form. So we're talking -6, 0 and 6, 0. All right. All intercepts, x-intercepts anyway, have y equals 0 in common. Every x-intercept, y is equal to 0. Okay, now the y-intercept, that's where the graph crosses the y-axis. That appears to be right here, and that point labeled would be 0, 3. And all y-intercepts have a 0 as an x value. All right, now we're back to increasing, decreasing, and constant. Let's write right on top of our graph. If you'll notice, this leftmost piece of the graph is increasing because it's rising from left to right. The piece in the middle is constant because it is completely horizontal, and the piece on the right is decreasing. Now remember, to answer this question, you use x values only. So for these three right here, you use x. So I'm trying to write over there, x values only. So you may want to label points. This point down here is -8, -3. Yes. This point right here is -4, 3. And this point right here is +4, 3. And there's no other points that are significant that we label. Now, we're only dealing with the x value, so we should only be looking at -8, -4, and 4 when we answer these questions. Okay? All right, so increasing, that's the one on the far left. It begins at -8, and it finishes, no, I wrote -infinity accidentally. It finishes at -4. Notice something about my interval, it's always smallest to largest, so I did that correctly. I went from -8 to -4. Y values don't matter. Okay? Constant. Okay? We're constant at -4 to 4. Again, the y values of 3 and 3, they don't matter. You begin at -4 being constant, and you end at +4 being constant. And then decreasing, you begin at +4 decreasing. Where does it finish decreasing? It doesn't. It goes down forever. So that's out plus infinity, the x value. Not the negative infinity, not the y value, just the x value. All right. And then the next question, H, the number in which f has a relative minimum. Remember, relative minimum is a valley. So is there any way we could hike down the valley and hike back up on the other side? Nope. This has none. Okay, not applicable, does not exist. Nowhere is there a relative minimum. Okay, so also none here. And you'll run into that sometimes. Okay, the value of x for which f of x equals -3. Okay, it's all about notation here, folks. This -3 value, that is a y value. So I'm asking you, what on the graph has y -3? Okay, so first of all, let's find y equals -3. I go to the origin and I count down 3 units. So anything along here at my red line is y equals -3. Okay, so I have a point on the graph right here, and I have another point on the graph right here. They're asking for the x values. So x equals -8 is one of my answers, and x is equal to, now let's figure out what that is. 1, 2, 3. So that's 8 right there too. I should have said 5, 6, 7, 8. Okay, so x equals -8 and x equals +8. have the same -3 y value. On the other hand, example question K is a completely different question. This is saying if x is -3, what is y? So both of these have -3 in common, but it's not the same question at all. Now I'm looking at x is equal to -3, so I count over to the left from the origin, okay, and -3 is right here, and I go to meet my graph, and that's right there, and that y value is 5. Finally, is this even, odd, or neither? Well, to me, at first glance, it looks very even. Okay, if I folded my piece of paper right down the y-axis right here, you would see that the right side folds over and matches up perfectly with the left side, except this part. This part that extends out here doesn't exist over here, and that means none or neither. It's not even nor odd. It was almost even. If I built a graph that kept going down like this, then you would have an even function. But since that doesn't exist right there, then you have a neither function. Okay, this is the last problem. I got a couple more problems to do for you on part 3 of the video. I'll see you in just a second.